By completing this course, you will be able to define 5G technology, discuss the need of 5G and the difference between 5G and the previous generation, describe the new features in 5G versus 4G, discuss 5G use cases, describe 5G requirement in terms of performance, low latency and high data throughput, discuss the requirement for a new network, define the organization involved in 5G standards, define the 5G standards timeline, describe 5G releases 15, 16 and 17. The first question. What is 5G? 5G is the fifth-generation mobile network. It is a new global wireless standard after 1G, 2G, 3G, and 4G networks. 5G enables a new kind of network that is designed to connect virtually everyone and everything together, including machines, objects, and devices. Why do we need 5G? Mobile data traffic is rising rapidly, mostly due to video streaming. Overall mobile data traffic is expected to grow to 77 exabytes per month by 2022, a seven-fold increase over 2017. Mobile data traffic will grow at a compound annual growth rate, CAGR, of 46% from 2017 to 2022. Mobile video content has much higher bit rates than other mobile content types. Mobile video will generate much of the mobile traffic growth through 2022. Mobile video will grow at a compound annual growth rate, CAGR, of 55% between 2017 and 2022, higher than the overall average mobile traffic CAGR of 46%. Of the 77 exabytes per month crossing the mobile network by 2022, nearly 61 exabytes will be due to video. Mobile video represented more than half of global mobile data traffic beginning in 2012. With multiple devices, each user has a growing number of connections. Another significant trend is the growth of smartphones, including tablets, from 50% share of total devices and connections in 2017 to over 54% by 2022. The most noticeable growth is going to occur in M2M connections, followed by tablets. M2M mobile connections will reach nearly a third, 31%, of total devices and connections by 2022. The M2M category is going to grow at 32% CAGR from 2017 to 2022, and tablets are going to grow at 14% CAGR during the same period. Along with the overall growth in the number of mobile devices and connections, there is clearly a visible shift in the device mix. M2M connections such as home and office security and automation, smart metering and utilities, maintenance, building automation, automotive, healthcare and consumer electronics, and more are being used across a broad spectrum of industries, as well as in the consumer segment. As real-time information monitoring helps companies deploy new video-based security systems, while also helping hospitals and healthcare professionals remotely monitor the progress of their patients, bandwidth-intensive M2M connections are becoming more prevalent. Globally, M2M connections will grow from just under a billion in 2017 to 3.9 billion by 2022, a 32% CAGR, a four-fold growth. Internet of Things will require networks that must handle billions more devices. The phenomenal growth in smarter end-user devices and M2M connections is a clear indicator of the growth of IoT, which is bringing together people, processes, data, and things to make networked connections more relevant and valuable. An important factor contributing to the growing adoption of IoT is the emergence of wearable devices, a category with high growth potential. Wearable devices, as the name suggests, are devices that can be worn on a person and have the capability to connect and communicate to the network either directly through embedded cellular connectivity or through another device, primarily a smartphone, using Wi-Fi, Bluetooth, or another technology. By 2022, there will be 1.1 billion wearable devices globally, growing over twofold from 526 million in 2017 at a CAGR of 16%. With a growing number of mobile and increased data traffic, both mobile and networks need to increase energy efficiency. Network operators are under pressure to reduce operational expenditure, as users get used to flat-rate tariffs and don't wish to pay more. The mobile communication technology can enable new use cases, for ultra-low latency or high-reliability cases, and new applications for the industry, opening up new revenue streams also for operators. So 5G should deliver significantly increased operational performance, for example increased spectral efficiency, higher data rates, low latency, as well as superior user experience, near to fixed network but offering full mobility and coverage. 5G needs to cater for massive deployment of Internet of Things, while still offering acceptable levels of energy consumption, equipment cost and network deployment and operation cost. It needs to support a wide variety of applications and services. .5G wireless technology is meant to deliver higher multi-gigabit per second peak data speeds, ultra-low latency, more reliability, massive network capacity, increased availability, and a more uniform user experience to more users. Higher performance and improved efficiency empower new user experiences and connects new industries. What is the differences between the previous generations of mobile networks and 5G? The differences between the previous generations of mobile networks and 5G. First generation, 1980s, delivered analog voice. Second generation, early 1990s, 2G introduced digital voice, CDMA code division multiple access. Third generation, 3G, early 2000s, 3G brought mobile data, CDMA 2000. Fourth generation, 4G LTE, 2010s, 4G LTE ushered in the era of mobile broadband. First G, 2G, 3G, and 4G all led to 5G, which is designed to provide more connectivity than was ever available before. 5G is a unified, more capable air interface. It has been designed with an extended capacity to enable next-generation user experiences, empower new deployment models and deliver new services. With high speeds, superior reliability and negligible latency, 5G will expand the mobile ecosystem into new realms. 5G will impact every industry, making safer transportation, remote healthcare, precision agriculture, digitized logistics, and more. How is 5G better than 4G? There are several reasons that 5G will be better than 4G. 5G is significantly faster than 4G, delivering up to 20 gigabits per second peak data rates and more than 100 megabits per second average data rates. 5G has more capacity than 4G. 5G is designed to support a multiple of 100 increase in traffic capacity and network efficiency. 5G has significantly lower latency than 4G, to deliver more instantaneous, real-time access, a multiple of 10 decrease in end-to-end latency down to 1 millisecond. 5G is a unified platform that is more capable than 4G. While 4G focused on delivering much faster mobile broadband services than 3G, 5G is designed to be a unified, more capable platform that not only elevates mobile broadband experiences, but also supports new services such as mission-critical communications and the massive IoT. 5G can also natively support all spectrum types, licensed, shared, unlicensed, and bands, low, mid, high, a wide range of deployment models, from traditional macro cells to hotspots, and new ways to interconnect, such as device-to-device and multi-hop mesh. 5G uses spectrum better than 4G. 5G is also designed to get the most out of every bit of spectrum across a wide array of available spectrum regulatory paradigms and bands, from low bands below 1 GHz, to mid bands from 1 GHz to 6 GHz, to high bands known as millimeter wave. Where is 5G being used? 5G is used across three main types of connected services, including enhanced mobile broadband, mission-critical communications, and the massive machine communications. A defining capability of 5G is that it is designed for forward compatibility, the ability to flexibly support future services that are unknown today. Enhanced mobile broadband. In addition to making our smartphones better, 5G mobile technology can usher in new immersive experiences such as virtual reality and augmented reality with faster, more uniform data rates, lower latency, and lower cost per bit. Mission-critical communications. 5G can enable new services that can transform industries with ultra-reliable, available, low-latency links like remote control of critical infrastructure, vehicles, and medical procedures. Massive machine communications. 5G is meant to seamlessly connect a massive number of embedded sensors and virtually everything through the ability to scale down in data rates, power, and mobility, providing extremely lean and low-cost connectivity solutions. In recent years, there have been several views about the ultimate form that 5G wireless technology should take. There have been two views of what 5G should be: hyper-connected view and next-generation radio access technology. Hyper-connected view. This view of the requirements for 5G wireless systems aims to take the existing technologies including 2G, 3G, 4G, Wi-Fi and other relevant wireless systems to provide higher coverage and availability, along with more dense networks. Apart from having requirements to provide traditional services, a key differentiator would be to enable new services like machine-to-machine, M2M applications, along with additional Internet of Things, IoT applications. This set of 5G requirements could require a new radio technology to enable low-power, low-throughput field devices with long battery lifetimes of 10 years or more. Next-generation radio access technology. This view of the 5G requirements takes the more technology-driven view and sets specifications for data rates, latency and other key parameters. These requirements for 5G would enable a clear demarcation to be made between 4G or other services and the new 5G wireless system. In order to meet the industry and user needs, it is necessary to accommodate all requirements within the definition process, ensuring that the final definition meets the majority of users' needs. The use cases and vision of the 5G system lead to diverse requirements that the future mobile broadband system will need to meet. The 5G unified ecosystem will serve both traditional as well as potential new applications, like drones, real-time video surveillance, mobile augmented and virtual reality, Internet of Things and so on. 5G will have to cope with a high degree of heterogeneity in terms of services, mobile broadband, massive machine and mission-critical communications, broader multicast services and vehicular communications. Device classes, low-end sensors to high-end tablets. Deployment types, macro and small cells. Environments, low density to ultra-dense urban. Mobility levels, static to high-speed transport. By accounting for the majority of needs, the following set of 5G requirements is gaining industry acceptance. High capacity and user rates. Low latency. High reliability. Ubiquitous coverage. High mobility. Massive number of devices. Low cost and energy consumption. One of the key issues with the 5G requirements is that there are many different interested parties involved, each wanting their own needs to be met by the new 5G wireless system. This leads to the fact that not all the requirements form a coherent list. No one technology is going to be able to meet all the needs together. As a result of these widely varying requirements for 5G, many anticipate that the new wireless system will be an umbrella that enables a number of different radio access networks to operate together, each meeting a set of needs. As very high data download and ultra-low latency requirements do not easily sit with low data rate and long battery lifetimes, it is likely that different radio access networks will be needed for each of these requirements. Accordingly, it is likely that various combinations of a subset of the overall list of requirements will be supported when and where it matters for the 5G wireless system. ITUR has defined the following main usage scenarios for IMT for 2020 and beyond in their recommendation, ITUR 2083. Enhanced Mobile Broadband, EMBB, to deal with hugely increased data rates, high user density, and very high traffic capacity for hotspot scenarios as well as seamless coverage, and high mobility scenarios, with still improved used data rates. Massive Machine Type Communications, MMTC, for the IoT, requiring low power consumption, and low data rates for very large numbers of connected devices. Ultra-reliable and low-latency communications, URLLC, to cater for safety-critical and mission-critical applications which requires different key capabilities according to ITUR 2083. So 5G should deliver significantly increased operational performance, such as increased spectral efficiency, higher data rates, low latency, as well as superior user experience, near to fixed network but offering full mobility and coverage. 5G needs to cater for massive deployment of Internet of Things, while still offering acceptable levels of energy consumption, equipment cost and network deployment and operation cost. It needs to support a wide variety of applications and services. The 8 key requirements along with some proposed target values are: peak data rate, maximum achievable data rate under ideal conditions per user or device. The peak data rate is expected to reach 20 GB per second, under certain conditions and scenarios. User experienced data rate. Achievable data rate that is available ubiquitously across the coverage area to a mobile user or device. In urban and suburban areas, a user experienced data rate of 100 megabit per second is expected to be enabled. In hotspot it is expected to reach higher values, for example 1 gigabit per second indoor. Latency, the contribution by the radio network to the time from when the source sends a packet to when the destination receives it. 5G will be able to provide 1 millisecond over-the-air latency. Mobility, maximum speed at which a defined quality of service and seamless transfer between radio nodes which may belong to different layers and/or radio access technologies can be achieved, in km per hour. IMT 2020 is expected to enable high mobility up to 500 km per hour with adequate quality of service. Connection density, total number of connected and/or accessible devices per unit area, per kilometer square. Network energy efficiency, referring to the quantity of information bits transmitted to or received from users, per unit of energy consumption of the radio access network, in bit-joule. It should be improved by a factor at least as great as the envisaged traffic capacity increase of IMT 2020 relative to IMT Advanced for EMBB. Spectrum efficiency, average data throughput per unit of spectrum resource and per cell, bit per second Hertz. It is expected to be 3 times higher compared to IMT Advanced for EMBB. Area traffic capacity, total traffic throughput served per geographic area, in megabit per second per meter square. IMT 2020 is expected to support 10 megabit per second per meter square area traffic capacity, for example in hotspots. The 5G wireless communications will be driven by three use cases of enhanced mobile broadband, massive machine-type communication, and ultra-reliable low-latency communication. The enhanced mobile broadband is designed for high-bandwidth internet access suitable for web browsing, video streaming, and virtual reality. The massive machine-type communication is responsible for establishing narrowband internet applications such as narrowband IoT. The ultra-reliable low-latency communication facilitates certain delay-sensitive applications such as factory automation, remote surgery, and autonomous driving. Of all the above technologies, ultra-reliable low-latency communication will be the most stringent to achieve based on the 1 millisecond end-to-end latency, link reliability of 99.99999% and error rates that are lower than 1 packet loss in 100,000 packets as recommended by the ITU. New techniques are required to meet with stringent latency and reliability requirements for ultra-reliable low-latency communication as we migrate into the domain of haptic communications, tactile internet, intelligent transport system, and Industry 4.0 era revolution. Latency specifies the end-to-end communication delay, measuring the time between the sending of a given piece information and the corresponding response. To give an example, latency can be identified in the time gap between the moment you click stop and the instant in which a remotely driven vehicle actually starts braking. Reducing the latency experienced by the end users from hundredths of a second to a few of milliseconds can have an unexpected impact, leading to a real digital revolution. Low delays achieved by the development of 5G-based mobile networks open the way to radically new experiences opportunities, including multiplayer mobile gaming, virtual reality experiences, factory robots, self-driving cars, and other applications for which a quick response is not optional at all, but a strong prerequisite. Focusing on self-driving vehicles, current cellular networks already provide a wide variety of tools that address some of the technology and business requirements. For example, LTE Category M and Narrowband Internet of Things are excellent low-power sensor communication technologies. However, in order to enable complex vehicle maneuvering, determining and recommending individual actions, for example acceleration, deceleration, lane changes, or route modifications, the vehicles must be able to share and receive information about their driving intentions in almost real time. This low latency demand certainly requires the development of an overall 5G system architecture to provide optimized end-to-end vehicle-to-everything (V2X) connectivity. Several emerging technologies including wearable devices, virtual and augmented reality, and full immersive experience are shaping the demeanor of human end users, and they have special requirements for user satisfaction. Therefore, these use cases of the next generation network push the specifications of 5G in multiple aspects such as data rate, latency, reliability, device and network energy efficiency, traffic volume density, mobility, and connection density. Current fourth-generation networks are not capable of fulfilling all the technical requirements for these services. Latency is highly critical in some applications such as automated industrial production, control robotics, transportation, healthcare, entertainment, virtual reality, education, and culture. In some cases, we need latency as low as 1 millisecond with packet loss rate no larger than 0.01. Several latency-critical services which need to be supported by 5G are described as follows. Factory automation includes real-time control of machine and system for quick production lines and limited human involvement. In these cases, the production lines might be numerous and contiguous. This is highly challenging in terms of latency and reliability. Therefore, The latency requirement for factory automation applications is between 0.25 milliseconds to 10 milliseconds with a very low packet loss rate. Intelligent transportation systems, autonomous driving and optimization of road traffic requires ultra-reliable low-latency communication. According to Intelligent Transportation Systems, ITS, different cases including autonomous driving, road safety, and traffic efficiency services have different requirements. Autonomous vehicles require coordination among themselves for actions such as platooning and overtaking. Road safety includes warnings about collisions or dangerous situations. Traffic efficiency services control traffic flow using the information of the status of traffic lights and local traffic situations. For these purposes, latency of 10 milliseconds to 100 milliseconds with low packet loss rate is required. Robotics and Telepresence. In the near future, remote-controlled robots will have applications in diverse sectors such as construction and maintenance and dangerous areas. A prerequisite for the utilization of robots and telepresence applications is remote control with real-time synchronous visual haptic feedback. In this case, system response times should be less than a few milliseconds including network delays. Communication infrastructure capable of proving this level of real-time capacity, high reliability and availability, and mobility support is to be addressed in 5G networks. Virtual reality. Several applications such as microassembly and telesurgery require very high levels of sensitivity and precision for object manipulations. VR technology accommodates such services where several users interact via physically coupled VR simulations in a shared haptic environment. Current networked communication does not allow sufficient low latency for stable, seamless coordination of users. Typical update rates of display for haptic information and physical simulation are in the order of 1000 Hz, which allows round-trip latency of 1 millisecond. Consistent local view of VR can be maintained for all users if and only if the latency of around 1 millisecond is achieved. Healthcare, telediagnosis, telesurgery and telerehabilitation are a few notable healthcare applications of low-latency tactile internet. These allow for remote physical examination even by palpation, remote surgery by robots, and checking of patients' status remotely. For these purposes, sophisticated control approaches with round-trip latency of 1 to 10 milliseconds and high reliability data transmission is mandatory. Serious gaming. The purpose of serious gaming is not limited to entertainment. Such games include problem-solving challenges and goal-oriented motivation, which can have applications in different areas such as education, training, simulation, and health. Network latency of more than 30 to 50 milliseconds results in a significant degrade in game quality and game experience ratings. Ideally, a round-trip time on the order of 1 millisecond is recommended for perceivable humans interaction with a high-quality visualization. Smart grid. The smart grid has strict requirements of reliability and latency. The dynamic control allows only 100 milliseconds of end-to-end latency for switching suppliers. However, in case of asynchronous co-phasing of power suppliers, an end-to-end delay of not more than 1 millisecond is needed. Education and culture. Low-latency tactile internet will facilitate remote learning and education by haptic overlay of teacher and students. For these identical multimodal human-machine interfaces, round-trip latency of 5 to 10 milliseconds is allowed for perceivable visual, auditory, and haptic interaction. In such scenarios, supporting network latency lower than few milliseconds becomes crucial. based on the applications and use case scenarios above. Latency critical services in 5G networks demand an end-to-end delay of 1 millisecond to 100 milliseconds. The latency requirements for various 5G services are summarized in the following table. Factory automation, 0.25 to 10 milliseconds. Intelligent transport systems, 10 to 100 milliseconds. Robotics and Telepresence, less than 1 millisecond. Virtual reality, less than 1 millisecond. Healthcare, 1 to 10 milliseconds. Serious gaming, 1 millisecond. Smart grid, 1 to 100 milliseconds. Education and culture, 5 to 10 milliseconds. The latency of LTE is superior to that of 3G, but still inferior to what can be achieved with the wired internet. LTE has 10 millisecond frame and 1 millisecond TTI, which are hard limit for latency. The new 5G subframe will be at sub-millisecond level, to set a base for short latency. Mobile broadband addresses the human-centric use cases for access to multimedia content, services and data. The demand for mobile broadband will continue to increase, leading to enhanced mobile broadband. The enhanced mobile broadband usage scenario will come with new application areas and requirements in addition to existing mobile broadband applications for improved performance and an increasingly seamless user experience. This usage scenario covers a range of cases, including wide area coverage and hotspot, which have different requirements. For the hotspot case, that is for an area with high user density, very high traffic capacity is needed, while the requirement for mobility is low and user data rate is higher than that of wide area coverage. For the wide area coverage case, seamless coverage and medium to high mobility are desired, with much improved user data rate compared to existing data rates. However, the data rate requirement may be relaxed compared to hotspot. The peak data rate of IMT 2020 for enhanced mobile broadband is expected to reach 10 gigabit per second. However, under certain conditions and scenarios, IMT 2020 would support up to 20 gigabit per second peak data rate. IMT 2020 would support different user-experienced data rates covering a variety of environments for enhanced mobile broadband. For wide area coverage cases, for example in urban and suburban areas, a user-experienced data rate of 100 megabit per second is expected to be enabled. In hotspot cases, the user-experienced data rate is expected to reach higher values, for example 1 gigabit per second indoor. The minimum requirements for peak data rate are as follows: downlink peak data rate is 20 gigabit per second. Uplink peak data rate is 10 gigabit per second. Peak data rate is the maximum achievable data rate under ideal conditions, in bit per second, which is the received data bits assuming error-free conditions assignable to a single mobile station, when all assignable radio resources for the corresponding link direction are utilized, that is excluding radio resources that are used for physical layer synchronization, reference signals or pilots, guard bands and guard times. Peak data rate is defined for a single mobile station. In a single band, it is related to the peak spectral efficiency in that band. User-experienced data rate is the 5% point of the cumulative distribution function, CDF, of the user throughput. User throughput, during active time, is defined as the number of correctly received bits, that is the number of bits contained in the service data units, SDUs, delivered to layer 3, over a certain period of time. The target values for the user-experienced data rate are as follows: in the dense urban environment, downlink user-experienced data rate is 100 megabit per second. Uplink user-experienced data rate is 50 megabit per second. Area traffic capacity is the total traffic throughput served per geographic area, in megabit per second per meter square. The target value for area traffic capacity in downlink is 10 megabit per second per meter square in the indoor hotspot, EMBB. Connection density is the total number of devices fulfilling a specific quality of service per unit area, per kilometer square. The minimum requirement for connection density is 1 million devices per kilometer square. Although 5G relies on existing network infrastructure and concepts, there are several new features to 5G. Such features new radio, NR, and new core 5G-C, operation in high-spectrum bands millimeter wave with massive MIMO antenna systems. The air interface between the G node B and user equipment, UE, has been named the new radio, NR. However, the interface between the NGE node B and UE remains the same as in LTE, Evolved Universal Terrestrial Radio Access, EUTRA. The G node BS and NGE node Bs are connected to one another via the new XN interface. The NR interface is designed to support multiple frequency ranges and bandwidths, low latency with flexible slots configuration, multi-gigabits per second data rates and increased spectral efficiency. The new Core 5G-C is a service-based architecture in which different network functions, providers, offer services to other NFs, consumers, through interfaces. The NFs can be placed at specific locations to fulfill certain latency requirements. This allows operators to deploy and adapt the network according to their needs. This network structure is a cloud-native, programmable, modular architecture designed to create multiple logical networks, or slices, running over the same physical or virtual resources. This design responds to the different network requirements of the different use cases. The technology behind this architecture is network functions virtualization and software-defined networking. A new spectrum needs to be introduced to ensure 5G meets the defined requirements. New frequencies will range from 450 MHz to approximately 50 GHz. High-frequency bands will deliver faster data rates and extended capacity, especially at millimeter wave bands, above 24 GHz. The Release 15 NSA specification defines the EUTRA, NR dual connectivity operation, whereby a UE is connected to one E node B acting as a master node and one NG node B acting as a secondary node. The NG node B is a node providing NR user plane connectivity to the UE and might be connected to the Evolved Packet Core, EPC, through the S1U interface. The E node B is connected to the EPC via the S1 interface and to the NG node B via the X2 interface. Network slicing. In 5G, not all traffic is equal. Mobile operators must be able to match different services with different levels of access. A concept known as network slicing. Many critical applications, such as autonomous vehicles and remote surgery, will demand prioritized 5G slices to guarantee a secured continuous service. The network will be sliced into multiple virtual networks running on a common network infrastructure, each with its own set of characteristics. A network slice is composed of a RAN and a core network with either physical or virtualized functions. Massive MIMO, multiple input multiple output aims to increase the number of transmitting and receiving antennas, TXRX, to have more signal paths and achieve gains in spectral efficiency. This would make it possible to provide higher capacity within the same spectrum. While conventional MIMO, as defined in LTE, uses few TXRX antennas, 5G goes further with massive MIMO by using dozens or even hundreds of antennas at the same time. Massive MIMO is expected to be used in the new millimeter wave frequencies, with rectangular antenna arrays in both the base station and the UE. MEC, Multi-Access Edge Computing. The 5G network architecture will support multi-access edge computing technology. MEC provides cloud computing capabilities running at the edge of the network, taking advantage of the low latency and high bandwidth provided by 5G. It is expected that MEC will foster the creation of innovative services and use cases such as video analytics, location services, augmented reality, data caching and optimized content distribution. The evolution from 4th G to 5G in the transport network. The introduction of 5G promises to deliver new capabilities and new technologies that include the use of higher radio frequency bands to support additional bandwidth millimeter wave, faster and more efficient fronthaul connections, more reliable and cost-effective timing, and more granularity in the distribution of network functions. Network Functions Virtualization, NFV, refers to the replacement of network functions on dedicated appliances, such as routers, load balancers, and firewalls, with virtualized instances running as software. NFV's purpose is to transform the way networks are built and services are delivered. With NFV, any enterprise can simplify a wide array of network functions, as well as maximize efficiencies and introduce new revenue-generating services faster and easier than ever before. "5G Nfv and Network Slicing." In 5G, NFV will enable network slicing, a virtual network architecture aspect that allows multiple virtual networks to be created atop a shared physical infrastructure. Virtual networks can then be customized to meet the needs of applications, services, devices, customers, or operators. In 5G, NFV will also enable the distributed cloud, helping to create flexible and programmable networks for the needs of tomorrow. The third-generation partnership Project 3GPP unites 7 telecommunications standard development organizations. ARIB, the Association of Radio Industries and Businesses, located in Japan. ATIS, the Alliance for Telecommunications Industry Solutions, located in USA. CCSA, China Communications Standards Association, located in China. ETSI, the European Telecommunications Standards Institute, located in France. TSDSI, Telecommunications Standards Development Society, located in India. TTA, Telecommunications Technology Association, located in Korea. TTC, Telecommunication Technology Committee, located in Japan. The role of these organizational partners is to approve and maintain the 3GPP scope, maintain the partnership project description, decide the creation or cessation of technical specification groups, approve their scope and terms of reference, approve organizational partner funding requirements, allocate human and financial resources to the project coordination group, act as a body of appeal on procedural matters referred to them. The 3GPP organizational partners may invite a market representation partner to take part in 3GPP, which has the ability to offer market advice to 3GPP, and to bring a consensus view of market requirements, like services, features and functionality, falling within the 3GPP scope. Does not have the capability and authority to define, publish and set standards within the 3GPP scope, nationally or regionally. The 3GPP project covers cellular telecommunications technologies, including radio access, core network and service capabilities, which provide a complete system description for mobile telecommunications. The 3GPP specifications also provide hooks for non-radio access to the core network, and for interworking with non-3GPP networks. 3GPP specifications and studies are contribution-driven, by member companies, in working groups and at the technical specification group level. The three technical specification groups, TSG, in 3GPP are Radio Access Network, RAN, Group to develop wireless access technology. Service and Systems Aspects, SA, Group for Service and System Architecture. And Core Network and Terminals, CT, Group for Core Network and Devices. Each group has smaller working groups, WG, for practical level development. The intergovernmental organization that manages global telecommunications affairs is called International Telecommunication Union, ITU, founded by the United Nations, UN, in 1865. ITU is responsible for issues that concern phone calls, satellites and the Internet. To manage various aspects of the matters, ITU is comprised of three sectors, including radio communication, ITUR. It covers the overall radio system aspects of international mobile telecommunications, IMT, systems, including 3G, 4G, 5G and future generations of wireless mobile telecommunications technology. The International Telecommunication Union, ITU, sets the main visions and goals while 3GPP develops the standards. In order to achieve this goal, ITUR established the concept of IMT, which includes a harmonized time frame for future development, taking into account technical, operational, and spectrum-related aspects. Since then, ITUR has been striving for harmonized global standards all through the process of IMT 2000, IMT Advanced and IMT 2020 standards. In early 2012, ITUR embarked on a program to develop IMT 2020, setting the stage for the 5G research activities that have since emerged across the world. The European Commission 5G research activities began in November 2012 with the co-funding of METIS. Mobile and Wireless Communications Enablers for the 2020 Information Society. The industry buzz on 5G increased dramatically in 2014. Attention was becoming more focused on establishing the operator's view of the enablers for a connected society in the 2020 and beyond timeframe. In 2015, the ITUR finalized its vision of the 5G mobile broadband connected society. Moving forward, the 3GPP starts working on a more detailed set of standards for 5G. Their initial focus is on setting requirements, followed by formal study items to baseline the architecture and radio technologies. This will lead to work items between 2017 and 2019 to define the complete 5G specification, resulting in the first release being issued as part of 3GPP Release 15. In March 2017, industry agreed on 5G NR acceleration. The accelerated schedule helped eliminate a perceived threat from market fragmentation. In December 2017, 3GPP approved the set of specifications which define the non-standalone NSA architecture option, which leverages the LTE and NR interfaces, as well as the existing LTE core network, EPC. Standalone NR operation is part of the final 3GPP Release 15 specification completed in June 2018. Full IMT 2020 compliance will be part of 3GPP Release 16, to be finalized in 2019. After initial delivery in 2017 of non-standalone NSA NR specifications for 5G, much effort focused in 2018 on timely completion of 3GPP Release 15, the first full set of 5G standards, and on work to pass the first milestones for the 3GPP submission towards IMT 2020. Release 15 focus is enhanced mobile broadband, and therefore all features are geared towards enabling the 5G system, Phase 1. Massive MTC and Internet of Things, IoT. Vehicle to Everything Communications, V2X, Phase 2. Mission Critical, MC, interworking with legacy systems. LAN and unlicensed spectrum use. Slicing, logical end-to-end networks. API exposure, third-party access to 5G services. Service-based architecture. Further LTE improvements. Mobile communication system for railways. The major characteristics of 5G, Release 15 Phase 1 that enable eMBB, from 10 GB per second to 20 GB per second, include ultra-wide bandwidth, up to 100 MHz in less than 6 GHz, up to 400 MHz in greater than 6 GHz. Set of different numerologies for optimal operation in different frequency ranges. Native forward compatibility mechanisms. New channel coding. Native support for low latency and ultra reliability. Flexible and modular RAN architecture, split fronthaul, split control and user plane. Native end-to-end support for network slicing. As the Release 15 work has matured and drawn close to completion, the group's focus is now shifting onto the first stage of Release 16, often referred to informally as 5G Release 15 Phase 2 feet. As the Release 15 work has matured and drawn close to completion, the group's focus is now shifting onto the first stage of Release 16, often referred to 5G Release 15 Phase 2. Ending July 3, 2020, Release 16 was completed with both the Stage 3 freeze and the ASN1 and Open API specification freeze being approved. The major focus in Release 16 is to enabling ultra-reliable low latency for mission-critical applications. The 5G system Phase 2. Enhancement of ultra-reliable, UR, low-latency communications, URLLC. Cellular IoT support and evolution. Advanced V2X support. 5G location and positioning services. UE radio capability signaling optimization. Enablers for network automation architecture for 5G. Wireless and wireline convergence enhancement. Mission critical, public warning, railways and maritime. Streaming and TV. User identities, authentication, multi-device, network, slicing. From a business angle, Release 16 enables applications for new vertical industries and deployment scenarios. Integrated Access and Backhaul, IAB. NR in unlicensed spectrum. Features for Industrial Internet of Things, IIoT, and ultra-reliable low-latency communication, URLLC. Intelligent Transportation Systems, ITS, and Vehicle-to-Anything, V2X, communications, positioning. The building blocks of 5G that enable URLLC include low latency, time synchronization, resource management, reliability. In 2020 Release 17. Study items for Release 17 are 5G up to 71 GHz and to explore new and more efficient waveforms for the 52.6 to 71 GHz band. 5G NB-IoT and eMTC. The objective is to develop cost-effective devices with capabilities that lie between the full-featured NR and low-power wireless access. 5G XR. The objective of this is to evaluate and adopt improvements that make 5G even better suited for augmented reality, virtual reality, and mixed reality. 5G non-terrestrial network, NTN, support for NR, NB-IoT and eMTC. A typical NTN is the satellite network. The objective is to address verticals such as mining and agriculture, which mostly lie in remote areas, as well as to enable global asset management, transcending continents and oceans.